This
Yes, sir.
conference will now be recorded.
So in the earlier class, I think Deepa was there. So Deepa, we had already discussed few things in this chapter, second chapter, measurements and units. So we had already learned what is parallax method, and using that parallax method, we can estimate the size of the celestial objects, and also we have seen how we can measure using the parallax method a very long distant object like planets, the distance of the planets and various stars, etc. So that was the parallax method. And length, which we cannot measure with our any physical instrument, can be done with that parallax method. So there are, see, there are three kind of fundamental parameters, three fundamental parameters, physical parameters, which are length, mass and time. So if we somehow can measure these three things, we can measure anything in this universe. Okay, so that's why in this chapter the three measurements, like measurements of three parameters, physical parameters like length, and length can be very large, okay, very large, that we can say distance, or very small like atomic size. Similarly, mass can be a very large, very small, etc. So we had already covered how we can measure the very large distance, but today we'll see how we can measure approximately any size of molecular, like any length of molecular size. See, nowadays we have many things, like many good instruments with which we can do measurement of smaller objects. Like, see, we have microscope, okay, with which we can measure the dimension, or we can see very small object, okay, small object, okay. But see, these microscopes are actually, I am talking about light microscope. So these are the microscope which you will be seeing in your school level laboratories, the biology laboratory. So where light has been used as the medium, okay, light has been reflected through the lenses, and which you see. So through that you see the smaller object, okay. But there is a limitation in this case, because see, light has certain wavelength, certain wavelength, and you will be learning in your higher classes that because of this wavelength, it has its resolution, some resolution, in the sense, suppose there are two lines over here, they are actually separated by a distance, very small distance, suppose d. If you look with something which has a dimension greater than this small d distance, then what you look, you look this thing as a continuous, so you will see this like this, okay. You will not see see these two lines separately. Okay, you'll not see these two lines separately if you use an instrument which has a resolution greater than resolution greater than d. Okay, that means it can measure a minimum length which is greater than d. That is called actually resolution. So if you take such instrument or such medium, like see, if my wavelength of the light is greater than the wavelength lambda is greater than this small d, then I cannot see these two lines separately. I mean to say, in the light microscope, we take the medium as light to see small objects, smaller objects. But visible light has wavelength 700 nanometer to 400 nanometer to 700 nanometer. So we can see objects in this range. Okay, we can see. Okay, so who is this? Vijay, sir, could you please say short notes on alternating current, please? See, Vijay, I'll tell you, but this is not a class of alternating current. But still, I'll say maybe last 5 minutes I'll take up your thing and I'll say something on alternating current. Okay, Vijay. Okay. So yeah. So this is about the resolution of light microscope. Now nowadays we have electron microscope. We have electron microscope. So with this also there are certain limitations. So to up to which we can measure smaller smaller distance. Okay. Obviously we have now in our modern science objects like which we can measure up to even few angstrom, not angstrom, maybe some even some 10 nanometer, 10 15 nanometer objects also, and near about 1 angstrom people can see atomic distance, like people can see there are instruments nowadays. But see, in the early days these sophisticated instruments were not there. But without using this kind of sophisticated instruments also, there is an approximate method with which in early days molecular size could be measured, especially for the oleic acid. Oleic acid molecules are actually very size, like bigger size. So molecular size of oleic acid actually is little bigger. Second thing is this oleic acid solution is is a soapy solution. Okay, soapy solution. And it can make a monolayer thin film. Monolayer thin film. Okay, so these are few things about oleic acid, and because of this second property, at least because of this second property, we can make use of this property to find out the molecular size of this oleic acid. So what is the procedure? We'll see it here. See, First of all, we have to make the solution of this oleic acid. Okay, just before I tell you about this oleic acid, molecular size of the oleic acid, uh, measurement process, I'll just tell you what is called monolayer thin film. Mono means one, so that you understand. So monolayer thin film means, suppose you have, molecules means you have, so molecules are actually taken as spherical in size. Okay, spherical in shape, spherical in shape. So there are three assumptions here. Molecular molecular shape is spherical, and monolayer will be produced. Like, if you have, see, if you have water over here, and if you just put uh, a oleic acid solution, see, they will spread over this water molecule and make a film in such a way that one molecule will be at a place, okay, at a single, like single molecule will be there at a single place. They will not overlap each other. It is not the thing here. Actually, they will make a monolayer film. That means these molecules will be just situated nearby, like this. Okay, like this. So they will create a film like this. So this is a film, thin film of monolayer. This is called monolayer thin film. Okay. So if it is not a monolayer, how it would look? If it is not a monolayer, it will be like this, like this. So this is a film. That means it can have many molecules in a single layer. Okay, on top of each other. So this is not a monolayer. But what I showed was is a monolayer. So this is actually assumption. Not only one assumption, oleic acid showed that. Okay, monolayer thin film. So now look, if I have a monolayer thin film, we will be able to estimate the size of molecular size of oleic acid. How? First, we have to make a solution. So how to make a solution? Solution of oleic acid. See, I'll take 1 cc centimeter cube in 20 centimeter cube. So this is oleic acid. Okay, in 20 centimeter cube. Okay, I'll just clean it here. I'll just write here. So making a solution. Okay, making a solution of oleic acid, of oleic acid. These are all step by step written in your book. You can see that. So first, 1 cc uh, oleic acid was put, or dissolve. I'll write dissolve in 20 cc alcohol. Alcohol. Okay, alcohol. Sorry. Okay. So so again, second time what had been done? See, this solution has been happened like now 20 ml. See, 20 cc oleic acid and alcohol solution. Among the, like, from this 20 ml solution, I'll take 1 cc solution now. Okay, This is not oleic acid purely now. Now you have 20 cc uh, oleic acid solution with alcohol. So that solution you take, okay, solution, and mixed, again dissolve this in 20 centimeter cube cc alcohol further. Okay, alcohol. Okay, so now what is the concentration of oleic acid now in this solution? So now I'll take 1 cc of this solution. Okay, this solution, 1 cc of uh, oleic acid solution in this solution. Okay, so I'll take 1 cc of this oleic acid solution. And what is the concentration in this? Concentration of concentration of oleic acid in this solution, how much it is? It is actually 1 over 20 into 20 cc. Okay, that means 1 by 400 c centimeter cube. This is the concentration. All right, this is the concentration. Okay, I hope you have understood this. If not, I'll repeat once again. So the solution was made by taking 1 cc or centimeter cube oleic acid. Okay, this is the volume of oleic acid mixed with 20 cc of alcohol. Then the solution you get, I take 1 cc from that solution and dissolve further with 20 cc alcohol. So I'm taking the final solution 1 cc, 1 cc of the final solution. So how much is the concentration then? 1 by 400 cc will be the concentration of oleic acid in 1 cc of the solution. Okay, now look, I have made the solution. I'll just screen everything. So what I know, concentration I know. Concentration, I'll just write it down in this corner. Concentration of oleic acid is 1 over 400 centimeter cube in 1 ce- centimeter cube solution. All right, this is the concentration. I have kept this information. Now what I'll do, after taking this solution in a burette, okay, very micro burette. Micro burette means you have burette having uh, this much 10 to the power minus 6 meter of the pore. Okay, that is very very thin pore. With that, what I'll do, see, I have kept a plate over here on which, like say, in plate, in this plate, I have kept water first. Okay, water, and then in the water, what has been given, some uh this is actually called uh some powder, lycopodium powder. Okay, lycopodium powder, lycopodium powder, powder, sprinkle sprinkle on the water surface. Okay, as you see from here, see, these small particles are what, see, on the water there are lycopodium powders. So lycopodium powders are very very light. Okay, so on the water it is actually covering the whole water surface. Now what we'll be doing, we'll be taking this solution, one cent, some amount of solution in the micro burette, and we'll just drop. Okay, will drop one by one on this uh, water surface of this plate. Okay, and what we have on the water surface, we have lycopodium powder scattered in that. Okay, all right. So when I pour the solution drop by drop, I'll count the drop. Suppose n drops dropped are dropped. Okay, and if I know volume of each volume of volume of each drop, v drop, actually volume of each drop is v, suppose. Okay, so then I know if I drop n drops, then what will be the total volume of the solution, oleic acid solution? The volume of dropped oleic acid solution, how much is that? N into v. This is centimeter cube. Then what is the concentration? How much is the amount of oleic acid we have? See, we had made the solution with alcohol, and you might be knowing that alcohol is actually uh, they have a uh, very much tendency to be evaporated easily. So when we drop cast this solution, after certain time, within, actually that will not take more than few seconds, alcohol will evaporate. Only what will be there on this water surface, that is oleic acid molecules. Oleic acid molecules. Okay, and so we need to know how many oleic acid molecules are there, or how much oleic acid molecules are there. What is the volume, or what is the concentration of the oleic acid in this dropped solution? So I know in 1 centimeter cube I have concentration 1 by 400. So in this much we will be having this. Okay, this is the this is the volume. Then concentration, concentration in this will be nv by 400. Okay, these are the, this is actually concentration or the amount of oleic acid. This is purely oleic acid after alcohol being evaporated. But what is the experiment here we are doing? See, when we drop this oleic acid drop by drop, what will happen? After dropping one drop, it will just touch the water surface, and then it will try to make a film. See, another drop will come and sit over here. Another drop will come, so this will sit over here. So if I drop another drop, that will come here and here and here. Like that, it will just make a film. And when it is actually making a film, see, the lycopodium powder was scattered on the surface. So that will be displaced by this oleic acid molecule. And finally, it will make a circular film like this. Okay, I'll show you here. Look, it will make a circular film on the lycopodium, see this water surface, where the lycopodium this powder will be displaced by the oleic acid molecules, and those molecules will be forming a thin film or patch here. Okay, that, yes, so this will be the size of the film. This is not a single molecule. This is not a single molecule. This is not a single molecule, but this is having many oleic acid molecules and monolayer. Okay, Monolayer means only one molecule is there. Okay, throughout the surface of this, throughout the surface. Okay, so if we can measure the diameter of this film, okay, this diameter of this film, then I can get the volume of that, okay, that film. I can get the volume of that film. Okay, so how do I get? I can just find out the volume, and I can, I'm sorry, volume I know already for the oleic acid. Okay, I know the volume. I can find out the area. I can find out the area. So once I see, I know the volume of the oleic acid. I know the area of the this particular uh, diameter thin film, and you know you have closed pack. So you can think that if I can find out the thickness of this film, then I get the diameter of only one molecule. You have to understand this physics, that what we are going to do here, we are going to measure the molecular size, okay, molecular size of the oleic acid. So for that, what we are doing, we are just dropcasting this oleic acid solution on the water, where lycopodium powder or on the water surface was there. As soon as you dropped some volume of that volume, the volume which I am just dropping here, I can know from the micropipette that graduations, okay, there you can measure. I know the volume, but this see, this oleic acid will form a thin film like a this circular film, and if I know, or if I can measure the diameter, I can get the area of this film. So I know the volume, I know the area. So generally volume is equal to thickness into area. So if I know the thickness, this film is actually monolayer film. So if I know the thickness of this film, then the diameter of I know the diameter of the molecule. So that is what will be done in this calculation. You look here in your textbook, it is already done. So look here. So the thickness of the film has been calculated. How? The volume of the film we have to find out. We know already this is the volume of the film, and you know the area of the film. Okay, just by noting down the diameter you see in your uh, glass, like that tray, volume of the film, sorry, diameter of the film. So once you know the diameter of the film, you get the area of the film, divide the volume of the film with the area, so you get the thickness. And as I told you, I'll just tell you once again, if we know the thickness, how we know the diameter of the oleic acid molecule, how you know? Look, I'll just show you. As I said, it is a monolayer film. Okay, you have, see, I'll just draw a monolayer film maybe here. Look here. So monolayer film means you have only one molecule like this. Okay, so I'll take this up to this. Okay, this is a monolayer film. Okay, if you know the thickness, see this thickness. If you know the thickness, so you know the diameter of the molecule itself. So that is what is being done here. We have just found out the or measured the diameter, thickness of this film. If we know the thickness of this film, then we know the diameter of the molecule. So this is what was the approximate method. That's why it is called estimation. Estimation in the sense it is not the accurate value. It can give you some estimation, some approximate value of the molecular size of this oleic acid. So this is actually this is actually uh, a good experiment, even though it is approximate method, but it is still useful and very good experiment. Now we'll see here. So this is the thing, you can just see this example as well after learning this. I hope you have learned this. So okay, so Deepa, do you understand this? Deepa, do you understand this?
Yes, sir.
Okay, good. So then, see, we have measurement of length of various, like see, various units are there like angstrom, then astronomical, see, we'll have light years, parsec, etc. So these are for very large. Angstrom, Fermi, these are for very small length. Okay, Fermi, Fermi or femtometer, 10 to the power minus 15 meter. Okay, and light year actually of 10 to the power 15. Okay, meter. Anyway, so parsec is the highest or the biggest, uh, I would say largest unit in length, parsec. Okay, you can, maybe you can know the order, 10 to the power 16 meter. All right. So see, there are measurements of mass and ranges of mass, etc. are there. This thing actually, if you read just like a story, you'll get few informations, and I hope there is nothing much like conceptually which will you will get stuck up with. If you don't understand anything, you can ask me, but I'm not going to teach these things here. You just read this, because just by reading you can understand. So there are, yeah, so there are much more important and conceptual things to learn. In even time measurement also there are no much conceptual things. If you read, you can understand. So what I'll do, I'll just directly go to this topic: accuracy, precision of instruments, and error in the measurement. So uh, in experimental physics or experimental science and technology, measurement is the basis, okay, or foundation. We do anything we learn or anything we say depends on our measurements, okay, or measuring values, measured values of any quantity. Okay, but in any instrument there are certain limitations, okay, some uncertainty, and because of that uncertainty we cannot measure any physical parameter exactly accurate. Okay, exactly accurate or exactly the same value we cannot get. So that's why it is said the uncertainty in the instrument actually is called error. Error does not mean that always you do. Error, actually instruments also does some error. We'll discuss how errors are coming into picture. Just before that, we'll say what is accuracy and what is precision. Okay, we'll learn what is accuracy and what is precision. Sorry. Just a minute. So let us learn what is accuracy and what is precision. Actually, accuracy means how close. See, every measurement has two values. Okay, every measurement has two values. What are those? One is true value true value, and another one is measured value. Measured value means whatever you get from the measurement. And see, these two values cannot be same in any time. So that's why error comes. Error is what is actually true value, true value minus measured value. Okay, or vice versa. So measured value can be fast like greater, or true value can be greater sometime. Okay, so error can be either positive or negative. Okay, so it can be, error can be positive or negative also. It doesn't have any like particular sign. Okay, so I hope you understood. I'll just give you one simple example also. Let me just tell you what is accuracy. Accuracy is actually, it is it is the value, or how close, how close uh, how close we can get the measured value, get the measured value to close, how close to the true value, true value. Okay, so that's what is called accuracy. Suppose I'll give you one example. Suppose I have some measured value. Okay, some say, I think you have in your book itself. I'll just cite that example. You look here. The accuracy is actually measurement. Is it a measurement how, like, see how close the measured value is to the true value. That is called actually the accuracy. And precision is called actually to what limit the measurement can be done. To what limit a measurement can be done. Okay, I'll just take this example that sub. Okay, I'll just go to my presentation. So this is actually how close. So accuracy means how close to the true value we can measure. Okay, then what is accuracy? Sorry, what is, I'll just erase. Okay, so accuracy is how close you can measure, how close the measured measured value to the true value. Then what is precision? To limit what limit a quantity can be measured. What limit a quantity can be measured. Okay, that means how, what is the smallest, or smallest value can be measured by an instrument. So this precision is related to your instrument, by an instrument. Okay, how how small you can measure, what is the limit of that. Okay, so these are actually called precision and accuracy. This is accuracy. I'll just give you an example. So accuracy means how close you can measure to the true value, and precision is to what limit a quantity can be measured by an instrument, or what is the smallest value we can measure with an instrument. I'll just give you simple example. Suppose I am just measuring uh, a length. Suppose there is an object and it has a length. Okay, this has a length of some 3.678 something like that, this much centimeter. Okay, now I take a meter scale. Okay, centimeter scale or meter scale, whatever. So which has precision. Okay, that means suppose you can measure smallest distance by this is 0.1 centimeter, smallest value. Okay, can be measured. This is called precision. Okay, or sometime it is called least count also. We'll see that. So if I take this kind of scale, suppose I get the value something like 3.5 centimeter. Okay, for this object. Okay, instead of getting the true value, I am getting how much? So this is suppose true value. This is true value. But what I get in the measurement is 3.5 centimeter. So this is first measurement with one scale. If I take another scale and do the measurement, another scale, this is first scale, and the second scale that has resolution or smallest smallest length it can measure is 0.01 centimeter suppose, and with this we measure this L to be 3.38 centimeter, something like this. Okay, so in this case, can you tell me which is having greater accuracy among these two measurements? Which one has greater accuracy? We said accuracy means how close to the true value is your measurement. So my 3.5 is close to 3.6. So this is actually accuracy will be greater. Okay, among these two, the greater accuracy is in this measurement. Okay, greater accuracy is there here. This is having greater accuracy than this one. Okay, than this one. Now come to the resolution of precision. Precision, as I said, the smallest distance you can measure with your instrument is called resolution or precision. So look here in the second scale, you have a capacity to measure smallest length of 0.01 centimeter, whereas in the first you can measure 0.1 centimeter. So since it can measure much smaller, like one order of magnitude lesser than this scale, so this has actually better precision or better resolution, better resolution. So this measurement is actually this has actually greater precision. But this the previous measurement was greater accurate. Okay, comparatively having greater accuracy. I hope you have understood this. What is accuracy and what is precision? Precision means the smallest value you can measure with an instrument, that is called least count also sometime we'll see, and this is called actually the precision, and how close you can measure a value is called actually how close to the true value you can measure is called accurate measurement or accuracy of that measurement. Okay, that is the accuracy. So I have learned what is called accuracy, what is called uh, precision. Now I will learn what is error. Okay, what is error in the measurement? I told right already, I had already written. So error is actually true value minus measured value, or vice versa. Okay, this is actually error, this is called error. And errors actually, depending on the source and nature of the errors are actually divided into two categories. Okay, broadly two, but you can say three also. So broadly two categories. So see, one, actually three categories I'll tell you. So one is constant error, constant error. So the classification of this, okay, classification of this error, okay. So you can have, depending on the nature and the sources of the error can be divided into three actually. This constant error actually, this means, the constant error in any measurement, constant error. So this error will be okay. So this error will be constant. Okay, constant in any measurement. Okay, this is called constant error. So if you ask me what is the example, sir, so this constant error, actually the source of constant error is the calibration of an instrument. Okay, calibration. If the calibration is wrong, calibration means what? You have an instrument. Suppose I take a simple example of thermometer. Okay, simple example of thermometer. You have thermometer. See, you have mercury in the thermometer, and that actually gets melted, and then it just expand in this glass, inside the glass capillary, right? Inside the glass capillary, the pulse raise. Okay, when the temperature is increasing, and it has certain calibration. That means suppose 1 degree. See, suppose 1 degree means some 2 centimeter length. Okay, 2 centimeter length. It will increase. Okay, so this is called calibration. Okay, if you can do it correctly, then it is fine. Then you will get like very precise measurement and temperature. So 1 degree temperature is indicated by increase in length of this mercury by 2 centimeter. So this is called calibration. Okay, this is called calibration. We do, in many cases we do calibration. Okay, many instruments we do calibration. So it can be due to the calibration. Okay, for a calibration, you set up some parameters and then calibrate the machine. So when those parameters for the calibration you have set up is not changed time to time, then your instrument will give you a constant error, either plus or minus some k with every value. Every value of the measurement you'll get a particular constant error. Okay, that is called constant error. Now errors are actually fundamentally two types. One is uh, systematic error. One is systematic error, and another one is random error. So this is random error. So systematic errors are actually those errors which appear in the same direction. Okay, tend to appear in the same direction. The errors which tend to occur in the one direction. That means the error can be either positive or negative, and that will happen every case. In every case, that is the situation. Okay, so these are called systematic error. Deepa, I'll just go another 10 minutes and I'll uh, stop the session. Okay, so be patient and hear this because these are important. Okay, if you don't understand immediately, you can stop me and ask me, sir, what is this? Okay,
Okay, sir.
so systematic. Okay, so systematic errors are those errors which tend to occur in one direction. That means either in positive or in negative direction. So these are called systematic error. And these systematic errors have some sources. Look from which sources we get systematic error. Like what are the sources of systematic error? That is instrumental error. We get from instrument. This we had already discussed due to uh, wrong calibration. Wrong calibration. Then it may be due to uh, due to mismatch of zero line, or it is called errors. Zero errors. Okay, so you have a vernier calipers. So your main scale zero and the zero of the vernier scale will not match. So that is called zero error. Okay, so this kind of things will occur in a same direction. That means it is always constant. Like it is either positive or negative. It can happen. Okay. Then another source for this systematic error is actually the imperfect experimental technique. Okay, experimental technique. So what is that? Suppose you want to measure the temperature, and the thermometer scale you are just putting below the armpit. Okay, so if the contact is not better or not good, you'll not get the correct temperature. Sometime what we do, sometime there may be like vibration of the experimental setup. There can be some fluctuations in some parameters. So those are actually imperfect techniques. Okay. Then I have third reason, personal reason. Okay. Personal reason is the experiment is done by some human being. Okay, some person. So he may have some problems. Like see, he may not be so serious, so careful in taking the parameters or measuring the values. He can be sometime casually sit, like he is just reading a here, reading some value here, but he may be seeing from this side. Okay, this is called parallax method. So due to parallax, you may uh, not be able to find out the exact value, or you cannot measure the true value. Some people have a tendency to like see things with an inclination. Okay, your inclination of head and all, sometime right hand side, sometime left hand side, or actually when you take any measurement you should see from here. Okay, from here your eye should be perpendicular to the measuring scale, then your measurement will be perfect, not from the side. So from side means it is parallax method, you are seeing some error in the measurement. Okay, and there can be any other external reason also for systematic error. So you have understood what is systematic error. Systematic error is the error which occurs in one direction. That means if it is plus, it will be plus always. If it is minus, it will be minus always. Okay, and in any measurements it will be minus. Okay, so systematic there are sources like see instrumental error, then imperfect experimental technique, personal error, maybe some other other errors are also there, like other sources are also there for uh, some external sources, like change in external conditions, like maybe the so external condition. So these are the sources of systematic errors. Okay, so how to remove this systematic error? So measurement has to be done. So this is a remedy. Okay, measurement has to be done. Has to be done many times. Many times. Okay, if you do a many time measurements and then take the average, that value is actually thought of true value, or the like see in each case the systematic error will be actually eliminated, because systematic error is happening in the same direction. In any measurement it will be going in the same direction. So if you just take two values, suppose one is m, measured value is m, another measured value is m prime. If you just take the difference, or you
Only
just
two.
take the average of this, yes, m prime divided by 2. So I'm taking two measurements, but you can take 10, 20, sometime like in practical case maybe some 50 measurements, or like more than that measurement has to be done, and then you take the average. So average means the error will be eliminated in each cases. Okay, so this is the scenario. Okay, so shall I discuss the random error today, or we'll take up that in some other day, like next day? Shall you take the random error also? I'll tell you.
Okay, sir.
It will not take more than. Okay, I'll let me just finish this random error first. Okay, then we'll stop. Okay, random error maybe some 2-3 minutes extra. Okay, so what is random error? Then there are actually many other errors also, which like there will be many like numerical problems from this error. Okay, you have to learn it properly. So so let us see what is random error. So we have main category systematic error and random error. So we have learned what is systematic error. Now learn random error. So random errors are those errors which occur irregularly. Okay, occurs irregularly. Sometime positive, sometime negative. Okay, so irregularly. Okay, occurs irregularly. Sometime positive. Okay, sometime negative. So you cannot predict this error. Okay, whether it is going to be more or less, positive or negative. Okay, so you cannot predict this actually, and this error actually occurs from many sources, like see uh, like see random fluctuation of voltage. Suppose you are doing some experiment with current, so random fluctuation of voltage, random fluctuation of voltage, temperature, then humidity. So this you cannot, like suppose when you started the measurement, temperature was all right, voltage was all right, but in between there is some fluctuation in this parameters. So this will actually introduce the error in that. Okay, then okay, So these are few things like this random error
Sir,
have almost equal chances for both positive and negative. Yes. Yeah, tell me. Yeah, we'll just stop it here, okay? So this is actually random error. Next day we'll learn what is absolute error, then absolute error, then what is relative error. Next day we'll learn this,
sir,
and then
only
we'll
two
learn
errors.
what is percent. Sorry,
Sir, only two errors.
only
Two,
actually two
two
types
errors.
of errors. Okay, these are there
Sir,
only two types of errors. Two types.
third, sir.
What is that?
Third error.
Sorry.
Third error.
What is third error?
Wrong errors.
That means what? No, I'm telling you that these are the types of error. There are many errors. Okay, there are many errors, but those errors are categorized or classified into two main category. One is systematic error, another one is random error. See, I told sources of errors are many. Like see, instrument, like our own problem, then experimental conditions. Okay, these are various sources of errors. But errors are actually categorized into mainly two categories. One is random, another one is systematic error. Okay, that is depending on the
Okay.
nature, depending on the nature of the error. That is actually depending on the nature of the error. In random error, you cannot say whether it is positive or negative, whether it is large or small. But systematic error, if it is small, it is in every instrument, like every measurement, it will be small. If it is negative in the systematic error, it will be always negative. Okay, but in this case, it can be either positive or negative. Okay, it depends on the situation. Okay, and these see all type of errors are actually calculated in some particular term. Those are absolute error, relative error, and percentage error. These are the mathematical 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 language. Okay, mathematical language, I'll say mathematical language to express error, to express, okay, to express errors. In fact, in our result, whenever we write any result, experimental error, you have to write errors with the result, and you can take the help of these three language to express your error with the result. Okay, I'll teach you what is called absolute error, how to express that mathematically, what is called relative error and how to express in terms of mathematical expression, and what is percentage error. I'll teach you in the next class. Okay, next class, maybe next Tuesday we'll meet again, so that day we'll
Okay,
learn
sir.
that. Okay, so
Okay,
I'll
sir.
stop it here, Deepa. Okay, okay then.
Okay, sir. Thank you, sir.